Hello. Okay, like it's easy to calculate the expected value from the probability distribution table like this. This is a probability distribution for from randomly choosing an answer, and you may remember this is how we do it. Or you may simply use this result. Expected value of x equals to the probability of success, even in this case. It's if you want to confirm this, you can do this. The point was you calculate the probability weighted outcomes. Outcome times probability, and sum them. So the mean is zero point 0.2. Then next, now we are going to study. So the mean is simple. There is nothing much to say about mean. Mean equals to the probability of success, and zero point 0.2. The mean is zero point 0.2, and there is no partial credit, so it has no meaning. Zero point 0.2 has no meaning. There is no partial credit, uh, like when you choose a wrong answer. So you have to interpret this number, zero point 0.2, the mean, as the probability of success, right? This is another example where the interpretation of the mean is different from a typical numerical random variable. Anyhow, next, now let's find the variance. Given the same probability distribution table and the mean is already calculated, so try to find the variance. Uh, it, it may take a little more time, but still should be simple enough. I will please pause the video and do the math. I will turn to the next page. 3, 2, 1. The variance is 0.16. Uh, Remember, what you do here is you calculate the squared deviation first. So deviation is outcome minus mean. 1 minus 0.2, 0 minus 0.2. And then take square to them. So you get 2 squared deviations. And you multiply probabilities to these squared deviations. So weighted squared deviation equals the square deviation times its probability. Square deviation times its probability, these numbers, sum of them equals the variance. So the variance is 0.16 in this case. 0.16 is the variance. And then what can we learn? Okay, we would like to work in a general setup. So uh, the the mean with general parameter p and 1 minus p equals to p, as we learned earlier. The expected value of x equals to the probability of success. But now, where the variance comes from, it is a little bit more complicated, but I'm doing the same thing. I'm following the same steps as before, as the numerical example before, but now with a general notation with unknown p, parameter p. So the same, outcome minus mean. Mean is p, outcome minus mean, and square. And it's a square deviation, and weighted square deviation is multiplied by p. So square deviation times probability. Square deviation times probability. So when you expand the squares and rearrange the terms, redo everything, then in the end, what you get is p times 1 minus p. Variance of x equals to p times 1 minus p. Right? You may go back here. We got variance of x equals to 0.16. This is, instead of going through these, you may use just p equals to 0.2 and use the formula to obtain the variance. There was an easy way if you knew this result. So the variance of a binary variable is p times 1 minus p. I would interpret this as probability of success times probability of failure, right? Again, we only need the parameter p here only. So as I said, if you know the parameter p, then you can calculate everything. You know everything about that distribution. So the one parameter describes everything about this any binary distribution. So in the variance 2. And I'm going to show you how the variance changes when the probability of success changes. So I consider probability of success at 0%, 10%, 20%, 50%, 80%, 90%, 100%. For each of the parameter value, the variance corresponding to the parameter equals to 0, 0.09, 0.16, 0.25, 0.16, 0.09, and 0. Now let's see a pattern. The smallest is 0 at the boundary, at the border, and it increases up to 0.5 and then decreases. So increases up to 0.25 and then decreases back again, and it's symmetric. Then what can we tell from this pattern? Say if p approaches to 0, the probability of success approaches to 0. That means the outcome will be almost certainly a failure, right? The probability of success is near 0. So you can predict. I know it will be failure, right? So you can predict the outcome, so there is little uncertainty. Uncertainty is very small. So because uncertainty is very small, the variance converges to 0. Always, most of the observations will be concentrated at failure, and there will be very few success. So the variability is very small. However, when probability becomes 0.5, the outcome is perfectly half and half. So that's the maximum variability. There is no concentration. It's bipolarized. So the variance is maximized when the success and the failure are equally likely. All right, it's the most uncertain case. You cannot predict. If you whatever you predict, you are going to lose. You are going to be wrong with 50%. So most unpredictable situation when p equals to 0.5. And finally, as p approaches to 100% again, then again it's almost certainly a success. So most of the observations will be at success, and there will be very few observations on failure. So the variance will be nearly 0. Will approach to 0 again. So this is the intuition behind the variance of a binary distribution. So you may use the intuition to understand the formula. Okay, so I have explained. So this is it. This is it for a binary distribution. So binary distribution is the simplest possible distribution model. When you have binary outcomes, there are only two possible outcomes from a random variable. Then you need only one parameter, and the one parameter explains everything: mean, variance, and the other probability. And in this case, especially, the mean should be interpreted more carefully. That's all about the binary distribution. And we are going to extend this binary distribution to the binomial distribution, the main distribution of this chapter, in the next video. So thank you for watching this video. See you in the next video.